Welcome to our exploration of intriguing mathematical ideas in today's podcast episode. Recently, an online debate erupted over a seemingly simple question posed by a teacher in a student's homework assignment. How many degrees are there inside a triangle, a quadrilateral, a pentagon, and a circle? This precise phrasing of the question sparked a fascinating discussion. The student's response to the question was unconventional and sparked controversy. She stated that inside a triangle there are 180 degrees, inside a quadrilateral there are 360 degrees, inside a pentagon there are 3 times the degrees of a triangle, and, most intriguingly, inside a circle there is an infinite number of degrees. 3 main perspectives emerged from this discussion. The first aligns with traditional geometry teachings. The degrees inside a triangle add up to 180, inside a quadrilateral to 360, and as we consider a circle, the concept of degrees diverges to infinity. The second view, which is the standard response expected by the teacher, starts with the triangle at 180 degrees and the quadrilateral at 360 degrees. It then considers the degrees inside a pentagon as 3 times that of a triangle and suggests 360 degrees for the circle, adhering to the conventional rules of geometry. However, the third perspective, which I find most compelling, offers a different interpretation. It suggests that if the question is framed as how many degrees inside the following shapes, and the teacher insists that a circle encompasses 360 degrees, then for consistency, the same logic should apply to a triangle and other figures. Thus, in the context of this question, the only logical answer from the 3 branches of reasoning would be the third branch, where each of the shapes mentioned in the question encloses 360 degrees. This perspective is rooted in the concept of homeomorphism in topology, which considers properties invariant under continuous deformations. By placing a point inside each shape and rotating around it, we can view every closed shape, triangle, quadrilateral, pentagon, or circle, as enclosing a full rotation of 360 degrees. This interpretation challenges the traditional geometric proofs taught in schools, where the sum of angles inside a triangle is shown to be 180 degrees through the construction of parallel lines or the use of alternate interior angles, while a semicircle is indeed 180 degrees. This new topological viewpoint suggests that when considering the full rotation around a central point, each shape effectively encompasses 360 degrees. In school, we learned to prove that the sum of angles inside a triangle is 180 degrees by constructing parallel lines or leveraging properties of alternate interior angles. We draw a ray from one vertex, parallel to the opposite side, creating an angle that, combined with the other 2 angles, forms a straight line or half circle. Since a full circle spans 360 degrees, a semicircle must be 180 degrees, proving that the sum of angles inside a triangle is 180 degrees. For a quadrilateral, we can draw a diagonal, dividing it into 2 triangles. Since each triangle contributes 180 degrees, the total sum of angles inside a quadrilateral is 360 degrees. Extending this logic, for a polygon with n sides, the formula for the sum of interior angles is given by. This concise formula neatly encapsulates the relationship between the number of sides and the total angular measure of a polygon. As we consider polygons with more sides, approaching the shape of a circle, this formula leads to the paradoxical conclusion that a circle, being the limit of a polygon as the number of sides increases indefinitely, would have an infinite number of degrees. Now, let's delve deeper into the third perspective, which is informed by modern topology. In this field, we study properties that remain unchanged under continuous deformations. All closed plane shapes that can be continuously deformed into a circle are topologically equivalent, enclosing the same angle of 360 degrees. This concept aligns with the idea that every polygon, when viewed through the lens of topology, encloses 360 degrees. The Poincaré conjecture, while not directly related to the problem of degrees inside polygons, also explores the concept of homeomorphism, but in 3-dimensional space. The conjecture remained unsolved for over a century until the brilliant yet reclusive mathematician Grigori Perelman proved it. Famously, he declined the $1 million prize for his proof, choosing to live a modest life with his mother in St. Petersburg. Perelman's story is a testament to the pure pursuit of knowledge and the fascinating depths of mathematical inquiry. It also highlights the importance of embracing alternative perspectives, like the student's topological view of degrees in polygons. The concept of homeomorphism in topology has far-reaching implications for various modern fields, including artificial intelligence, machine learning, and neural networks. By understanding the principles of continuous deformations and invariant properties, we can tackle complex challenges in these cutting-edge domains. While the assertion of 360 degrees inside a triangle may seem provocative initially, we can appreciate its validity through the lens of topology. By embracing this alternative viewpoint, we open our minds to new ways of thinking and unlock deeper insights into the captivating world of mathematics. Before we conclude, allow me to extend an invitation. We traditionally end our podcasts by inviting you to listen to an AI-generated melody inspired by the theme of our discussion. So sit back, relax, and let the harmonies of artificial intelligence envelop you. Thank you for joining us on this thought-provoking journey. If you found this episode insightful, don't forget to subscribe and share it with others who appreciate the beauty and complexity of mathematics. Stay tuned for more captivating explorations in our future episodes.
Triangles and squares, shapes floating everywhere. Measure angles, you'll see. Some goes to 360. Circles swirling around. Lines connect on the ground. Corners to the centers. All add up, no pretenders. Every shape we see, it's all 360 degrees. No matter big or small, they follow this call. Hexagons and more, they all dance on the floor. Angles twist and they spin. 360 they begin. Look inside the square. 4 corners show us where. 90 each gives the clue. 360 shines through. Every shape we see, it's all 360 degrees. No matter big or small, they follow this call. Up in the AI top, where the future is now. Today, let the rhythm of progress lead you somehow. Imagine the soundscape that pulses innovation, a melody that defies all limitation. We're breaking barriers, we're pushing the line, exploring new frontiers.